Your heart is an absolute workhorse. I mean, it beats something like 100,000 times a day in and day out, and you never even have to consciously think about it. But underneath that steady rhythm, it's a literal masterclass in bioengineering. So let's just jump right into this explainer. Today, we're going to completely decode the cardiac cycle. We'll be looking at the exact timing, the pressures, and the fluid volumes that literally make human life possible, frame by frame. And the magic number here is zero point 0.8. At a normal resting heart rate of about 75 beats per minute, it takes exactly zero point 0.8 seconds to complete one full cardiac cycle. Just let that sink in for a second. In less than a single second, your heart manages this incredibly complex sequence. It fills up, builds immense pressure, ejects blood out to your entire body, and then completely resets itself, just to do it all over again. This zero point 0.8 second window is meticulously divided up. 0.1 seconds for the atria, 0.3 seconds for the ventricles, and exactly zero point 0.4 seconds for a total reset.
Here's our quick agenda for today. First, the 0.8 second miracle. Then, atrial systole, the primer, followed by ventricular systole, the pump. Next is ventricular diastole, the reset. And finally, we'll wrap up with the big picture.
Okay, section 1, the 0.8 second miracle. Before we zoom in, it helps to see how the systole, which is the contraction phase, and the diastole, the relaxation phase, visually intertwine. The heart's valves are acting as these perfectly timed gateways here, absolutely ensuring that blood only ever flows in one direction. It's essentially a beautiful, continuous dance of mechanical forces that perfectly maps out our zero point 0.8 second journey.
Moving right along to section 2, atrial systole, the primer.
So how do the main chambers actually fill up? Well, the filling of the ventricles is a 3-step process. It starts with rapid passive filling and ends with a final active contraction, which we call atrial systole. Initially, the intraventricular pressure drops all the way down to 0 during relaxation, so blood naturally just rushes in from the atria. That's your rapid filling. As that pressure difference starts to balance out, the filling naturally slows down. And then finally, we hit the active step, the actual contraction of the atria themselves. And remember, that takes a lightning-fast 0.1 seconds. The really crucial takeaway here is that this atrial contraction acts like a final kick to completely top off the ventricles with blood. When the atria contract, they generate what's known as the fourth heart sound, or S4, and they force that very last remaining bit of volume down into the main pumping chambers. Now, the pump is officially primed. In physiology, we call this the end diastolic volume, or EDV. In the left ventricle, this amounts to roughly 120 milliliters, so about half a cup of liquid. Think of it as a fully loaded spring, totally primed and ready for the main event. At this point, the filling phase is completely done. The ventricles have stretched out to accommodate all this blood, and that stretch is absolutely vital. Why? Because the more those muscle fibers stretch during this filling phase, the more forcefully they're going to snap back and contract. Let's look at that contraction in section 3, ventricular systole, the pump.
There's a brilliant mechanical contrast happening right here. First, the ventricles contract with all of their valves completely closed to build up massive pressure. This takes about 0.3 seconds in total. And then, the valves finally burst open to eject the blood. It's essentially a 2-part punch. You see, you can't just push the blood out immediately. You have to build up enough force first to overcome the heavy pressure of the entire circulatory system waiting on the other side.
And because all the escape routes are blocked by those closed valves, the internal tension just skyrockets without a single drop of blood actually leaving the chamber. We call this isovolumetric contraction. Iso simply means equal, and volumetric refers to the volume. The muscle is squeezing violently, and the intraventricular pressure is rapidly exceeding the atrial pressure. That pressure spike is what causes those atrioventricular valves to snap shut. But since the exit valves aren't open quite yet, that full 120 milliliters of blood is trapped, so the pressure just goes up and up and up. It's pretty wild when you look at the pressure gradient. The left ventricle actually has to generate 5 times the pressure of the right ventricle. It has to hit a massive 125 millimeters of mercury, which, by the way, is exactly what your doctor measures as the top number when taking your blood pressure. It needs that much force just to propel blood to your brain, your toes, and literally everywhere in between. Once the pressure inside the ventricles exceeds the pressure waiting in the aorta and the pulmonary artery, the exit valves are forced open. Now, the right ventricle only needs to hit about 25 millimeters of mercury to push blood into the nearby lungs. But man, that left side is working on serious overdrive. So of that original 120 milliliter payload we talked about,
The heart ultimately ejects a stroke volume of about 70 milliliters. That means it normally empties about 60% of its contents per beat. This 70 milliliters is the vital payload that actually leaves the heart to deliver oxygen to your tissues. And that percentage, the amount of blood pumped out compared to what it started with, is called the ejection fraction. So at rest, a healthy heart is basically operating at about a 60% efficiency rate per beat. Which brings us to section 4, ventricular diastole, the reset. Immediately after that forceful ejection, the interventricular pressures suddenly plummet right back down to zero, causing the aortic and pulmonary valves to slam shut. The ventricles stop contracting and they start to relax, and as they do, the pressure drops incredibly fast. Because the pressure in the aorta and pulmonary arteries is now suddenly higher than it is inside those relaxing ventricles, the blood naturally tries to flow backward. But in a perfectly designed mechanical catch, this backward flow catches the cusps of the exit valve and abruptly slams them closed. This absolutely crucial reset phase takes about 0.4 seconds, which is literally half of the entire cardiac cycle. Now, the mechanical shutting of these specific valves is what translates directly into that famous lub-dub audio signature you hear if you listen through a stethoscope. The first heart sound, the lub, or S1, is simply the atrioventricular valves shutting at the very beginning of the contraction. The second heart sound, the dub, or S2, is those aortic and pulmonary valves slamming shut right as the relaxation phase begins. So you aren't actually hearing the muscle squeeze at all. You are quite literally hearing the mechanical doors of the heart snapping shut. It's actually highly efficient that the heart doesn't completely empty itself out. Keeping a 50 milliliter reserve volume prevents the chamber walls from collapsing in on themselves. We call this remaining pool the end systolic volume. Remember the math? We started with 120 milliliters, we pumped out 70, and we are perfectly left with 50. Leaving this volume acts as a structural buffer. It keeps the ventricle primed and open, totally ready to accept the rapid inflow of blood the second the cycle starts over again. Let's wrap things up with section 5, the big picture. The math here balances out perfectly every single time, which really demonstrates the heart as an incredibly reliable, perfectly sealed mechanical pump. End diastolic volume minus end systolic volume equals your stroke volume. 120 minus 50 equals exactly 70. This very elegant, simple equation is the entire foundation of our cardiovascular output. And it happens over and over and over again. And so, the 0.8-second cycle just loops right back to the beginning, relentlessly pacing our existence without us ever having to consciously think about it. Literally, by the time I finish the sentence, your own heart has likely cycled through this entire miraculous process of filling, building pressure, ejecting, and completely resetting 5 or 6 times. It really is the ultimate precision engine. But I want to leave you with this. Think about what happens to this delicate timeline when your tissues suddenly scream for more output, forcing the heart to completely rewrite its own rules of timing and pressure. When you start running, your heart rate might double. That means this entire 0.8-second cycle has to instantly condense into just 0.4 seconds. How on earth does the heart fill completely in half the time? How does it manage to pump even more than 70 milliliters per beat to meet that new demand? It's a truly fascinating question of physiological adaptation, and it highlights just how dynamic and responsive this 0.8-second miracle really is. Thanks so much for joining me on this explainer, and keep wondering about the incredible engineering happening right inside your chest.